Hi, good morning everybody. So, today we will continue with complex reaction. So, last in our last discussion we finished with this Lindemann mechanism. So, I did not give any concrete example, real day example of a reaction where Lindemann mechanism is operative. So, let us take one example, that isomerization of trans deuteroethylene like C D so it isomerizes to cis form like this. So, this is found to follow Lindemann mechanism, and it shows the pressure dependence, like if this is 1 by K and if this is 1 by A, that is concentration of A, then it is found to follow like this, it deviates from linearity when pressure is increased. Okay. So, under low pressure condition means you introduce from outside some inert gas which does not take part in reaction. So, in that case partial pressure decreases, partial pressure of these molecules will decrease, and as a result of which it is found that it follows when pressure is less, I mean partial pressure is in this region. So, when partial pressure decreases this way, so it is found to follow a linear trend, but while in high pressure region it is found to deviate significantly from linearity. Okay, so this is one example where this Lindemann mechanism, this is also called Lindemann-Hinschel-Wood mechanism. In 1921 this was proposed. Next we will move on to chain reactions. Chain reactions means a reaction which which is having a number of steps, like one step then another step then another step, so which occurs in a chain. So, it is a sequential event. So, like this step then another step then another step and so on. So, this is a typical schematic of a chain reaction, like A to B then C then D. So, it's like a consecutive reaction, but it is a complex one. It is not a very simple one, but it is a complex one. Let us take one example, that decomposition of acetaldehyde producing this ethane, okay, then methane and also carbon monoxide. So, CH3CHO, it produces first this CH3 radical and CHO radical. This mechanism is proposed in this way, and then the CH3CHO again reacts with another CH3 radical producing CH4, that is this one snatches one hydrogen from here producing CH3CO radical and CH4, then CH3CO producing CH3 dot and CO. So, these two steps are called propagation, that is it is propagating, this chain reaction is being propagated. So, this is the starting point. So, it is called the initiation reaction, initiation step, that is this elementary step is initiation step, and here you see two CH3 radicals, okay, they combine to form this ethane. So, whatever CH3 dot was produced, CH3 radicals were produced in the initiation step and maybe in other steps, they are basically consumed to produce ethane. So, that is why it is called the termination, as if the reaction is terminated over here, no further reaction should take place, like that. Okay. So, now two types of chain reactions may be possible. One is a like I have drawn over here. So, it is a straight chain reaction. Another could be a branched chain reaction, like starting point and then it is doing like this, then it is further branched like this and so on. And you see, as time is passed by, too many steps are coming into action. Okay. So, as a result of which you see, products initially, if you start from here, only 2 steps, here it is 1, 2, 3, 4, 5, 6, 7, 8. So, it increases enormously. Okay. So, this type of situation is called the branching of chain, it is called the branching of chain. So, it is branched, chain is branched, but this one is a straight chain reaction. Okay. Now, let us take one example of this hydrogen plus bromine reaction producing HBr, H2 plus Br2 giving rise to HBr. Okay. So, it is found that rate of production of HBr has got a very peculiar dependence on H2 concentration, Br2 concentration and also HBr. Okay. So, let us write that and we will try to find out how this is coming. So, d dt of HBr, rate of production of HBr is equal to some constant H2 Br2 to the power 3 by 2 divided by Br2 plus another constant K primed HBr. Okay. So, this reaction if you write like this, if you rearrange it, then K into H2 then Br2 to the power half divided by 1 plus K primed into concentration of HBr divided by concentration of Br2. Okay. So, you see that this rate of production of HBr is proportional to the concentration of H2 and it is Br2 to the power half. So, it is fractional order. If you neglect this one, say if you neglect this one, or maybe if you do not think right now about the denominator, the numerator you see that it has got a to the power half dependence. So, fractional order with respect to Br2. Okay. So, that means earlier I talked about 0 order, first order, second order, third order and nth order, but here we are seeing that it is a fractional order. So, order is an experimentally determined quantity and it can be fractional. Okay. So, it is an important insight. So, let us look into the mechanism that was proposed independently by Michael Polanyi and Christiansen and Hirschfeld. So, mechanism goes as follows. So, Br2, if you look into this slide, you see first is Br2 producing 2 Br dot. So, it is the initiation step. Okay. So, if the rate constant is K1 for this process, then for the first one rate of production of this 2 Br dot is K1 times concentration of Br2. Then there are other steps like Br plus H2 producing HBr plus H dot, then H dot, this H dot is used up, okay, to produce HBr and Br dot, and then H dot again reacts with HBr, okay, to produce H2 plus Br dot. You see, if you look into the this scheme, I mean this expression, you will be seeing that this HBr is in the denominator. So, if HBr increases, rate of production of this HBr will be reduced. So, this may be this can be regarded as that step which is responsible for the inhibition, or it is acting as an inhibitor for the process. Okay. So, H2 plus Br dot, it is producing H2 plus Br dot. So, corresponding rate is like this, and then it is the termination Br dot plus Br dot. So, that is the back reaction of this, okay, producing this one Br2. So, the corresponding rate is this. So, these are the rate laws, and these are the corresponding elementary steps. Okay. So, since these are elementary steps, so therefore, the species which are involved in the elementary step can be directly involved, can be directly written in the corresponding rate expression. Okay. So, again what I told that this is initiation, as I told you, this is your propagation. Why propagation? Because this reaction produces one H dot, because the active ingredient for the reaction to proceed further is the radicals. So, here the active ingredients will be your Br dot and H dot. So, this Br dot produces another H dot, and this H dot again reacts with another bromine molecule to produce HBr and Br dot. So, whatever Br dot was involved, was utilized in this K2 step, is again generated through K3 step. So, these two are basically propagating this reaction. Okay. So, reaction I mean the process remains alive because of these two propagation steps. So, remember this initiation step requires a homolytic cleavage of this Br bond producing Br dot. Okay. So, this homolytic cleavage may be done various way, maybe thermally or maybe photochemically. So, these specific situations we may discuss later on. Okay. Now, next is inhibition step. As I told you that in the rate equation, in the denominator you can see one HBr concentration. So, when HBr concentration increases, so overall production of HBr is also reduced, because this HBr is again used up to produce H2 and Br dot. So, this is some kind of this back to this reaction, back of this reaction, back step of this reaction, backward reaction. Okay. So, that is why it is called the inhibition. It is acting as a kind of inhibition to the forward process. Okay. And this is the termination step. So, what we should do is making steady state approximation, applying steady state approximation, as I told you in our last lecture, that we have to apply steady state approximation to this active ingredients, like active species which are responsible for your for the process to carry forward. So, therefore, this is one Br dot. So, ddt of Br dot is this expression, and ddt of H dot is this expression. How this is coming? So, this is coming like ddt of Br. So, it is the rate of formation of Br dot. So, this is the first step. So, K1 Br2, then this K2 Br dot H2 with a negative sign, because this is used up. Then it is produced, Br dot is produced, that means it will be K3 H dot Br2, K3 H dot Br2. Then here Br dot is again produced, although this is an inhibition step, but it is Br dot produced. So, therefore, K4 H dot HBr. So, K4 H dot HBr with a positive sign, and it is the termination step. So, Br dot is used up, therefore, K5 with a negative sign into Br dot whole square. So, and you have to apply this equal to 0 for your steady state approximation. In the same way, d dt of h dot will have this expression, and you have to put this to 0 in order to have your steady state approximation applicable. Now, overall rate of production of HBr, because we are interested in finding out the rate law for the production of HBr. So, HBr is our product, H2 plus Br2 producing HBr. Okay. So, d dt of HBr will be equal to, so you just have to find out where this HBr is involved. So, these are the 3 steps where HBr has been involved. So, step B, C and D, these are the 3 steps where HBr has been involved. So, here HBr is produced means, so you have to write K2 Br dot H2, so with a positive sign. So, K2 Br dot H2. Okay. Here also it is produced, so that should also be with plus K3 H dot Br2, but here it is in acting in opposite direction. So, it will be minus K4 H dot HBr. So, since these are all elementary steps, you can directly put this concentration terms occurring in the left hand side, because it is it is occurring from left to right. So, reaction is proceeding to the right. So, your starting ingredient should be used in your rate expression. Okay. So, we have got 3 key equations, of which the last 2, this one and that one, these 2 should be equated to 0 because of this steady state approximation, and that whatever expressions for the concentration of H dot and Br dot, that we should put in the first expression, which is for the rate of production of HBr. Okay. So, after a steady state approximation is applied, we can find directly that Br dot, concentration of Br dot from steady state approximation will be K1 divided by K5 whole to the power half into Br2 whole to the power half. Okay. H dot, it will be a little complicated because it involves many steps, but Br, Br dot is a simple one, equal to H dot is equal to K2 times K1 by K5 to the power half times H2, then Br2 to the power half divided by K3 Br2 plus K4 HBr. Okay. So, if you plug in these 2 in the first expression, which is for your rate of production of HBr, so that is d dt of HBr, then it will be, you have to plug in these 2 onto the expression that we have, okay, and we will be getting 2 K2 K1 by K5 to the power half H2 Br2 to the power half divided by 1 plus K4 by K3 HBr by Br2. So, it is an example which has, it is a chain reaction. Of course, it is a radical chain reaction, of which one is initiation, another 2 are propagation, the 4th one is inhibition, and the 5th one is termination. So, considering all this and also invoking the steady state approximation onto H dot and Br dot, okay, which is a requirement of while treating these complex reactions. Okay. So, after plugging in this respective expressions to the expression of HBr, that is the respective expressions for H dot and Br dot to the expression of rate of production of HBr, we got this one, this particular expression, which says that the rate of production of HBr has got a fractional dependence, concentration dependence on Br2, and also as more of HBr is produced, so forward reaction is little bit inhibited, as evident from the mechanism. Explosion. So, what is meant by explosion? Explosion is this can be thermal explosions. Okay. So, rapid increase in reaction rate with temperature, which is called the thermal explosion. Okay. Or explosion may happen as a result of chain branching. Okay. So, chain branching, when steps into the mechanism, that will lead to a huge, maybe exponential increase in the number of chain carriers in the system. Okay. That means, as I showed to you like this, So, it is a huge increase. So, initially 1, then 2, 2 becomes 4, 4 becomes 8, and so on. Okay. So, it increases hugely, okay, and that leads to explosion. Okay. That leads to explosion. So, this is the schematic, that it is a straight chain reaction, it is a branched chain reaction and leading to explosion. Okay. So, basically if you do a simple experiment that you fill a container with hydrogen gas and then you try to burn it, okay, with a flame, then it will just explode. So, this production of hydrogen, I mean water from H2 and O2 through burning, okay, is an example of explosion. Okay. So, this is a typical H2 O2, H2 plus O2 producing 2 H2O kind of it's a situation. So, this is the plot, okay, plot of P versus temperature. Okay. So, now this is the region where chain branching and explosion happens, and here thermal explosion happens. Okay. And in this pressure region, it is a steady, this is your steady reaction region. Okay. And these are the three explosion limits. One is the first explosion limit, which is in between 2 to 3 Pascal. I mean log P, where P is written in P is expressed in Pascal. Okay. So, 2 to 3 there is one limit, then 3 to 4 one limit, and there is in between 5 and 6, it is the third explosion limit. Okay. So, this corresponds to maybe a 3 body collision, and this corresponds to recombination onto the walls. Okay. Now, the mechanism is like this, that H2 plus O2, this is the initiation step, H2 plus O2, okay, producing 2 OH dot OH radical. Then this OH radical will again react with H2 to produce water and a hydrogen, single hydrogen, monohydrogen, hydrogen atom. So, and this is the fast process, that is the propagation. Then this H dot, once it is generated through this fast propagation, so it will react with O2 to produce OH dot and O with 2 electrons. So, it is a slow, it is called the branching, but this process is slow. Okay. Another step is fast, and which is also branching, is O double dot plus H2 producing OH dot and H dot. So, it is with K4, and recombination at the wall, H dot plus wall means it collides with the wall to produce what I mean hydrogen back. It is called the termination. This is one termination step. There could be another termination step, that H dot plus O2 producing HO2 dot, while M is another component, another molecule present there, okay, molecule or maybe another entity. Okay. So, producing this is also a termination. Okay. Now, so what is the key step for this? So, we have to look into these two. So, this is your termination step, this is one important step, okay, and this is the slow one, because these two are fast. This occurs very, with time it occurs very fast, it does not take that much of time. Therefore, overall process will depend very much on the competition between this step C and step E, that is the third and fifth step. Now, when P is reducing, that is under low pressure condition, so step C is slow and step E is fast. Okay. So, under low pressure condition, what is happening, that this molecule, this oxygen molecule, okay, since they are rarefied under low pressure, means maybe some inert gas is present, or maybe if pressure is low, means these gas molecules are rarefied. So, the average distance between these molecules are more. Therefore, the probability of this collision, so this process will be less. So, therefore, it becomes slow, but this will be fast, because since this is occurring slowly, therefore, these molecules will get chance to collide with the walls, therefore, producing this. So, termination will win. So, it will be a non-explosion situation. Okay. Next is when P increases, what is happening? Step C goes up, because naturally if this is reducing, whatever situation is happening over here should be reversed over here. Okay. So, when P increases, step C tends to go up and step E tends to go down. Why go down? Because these oxygen molecules will get chance to collide with H dot. So, therefore, less number of H dot will remain in the reaction mixture to collide with the wall. Okay. So, what will happen, that it will be an explosion situation. Okay. So, that means branching will happen, this branching will take place. At the moment branching will take place, means you will be getting enormous number of chain carriers. Okay. So, it will so here it is 4, then it will be 16 and so on. It will increase very rapidly like an exponential function. Okay. Therefore, this will lead to explosion. P is still higher, what will happen, that in that case maybe step F, that is the last step shown over here as the termination step, this will be very important under that condition. Okay. So, this will be important, means these will be used up, that is this hydrogen dots will be scavenged by O2 with the help of another molecule or another entity M. So, it is another termination step. So, it will be again non-explosive. When P is very high, go back to this slide, very high, above third explosion limit. Okay. So, where HO2 dot, this whatever HO2 dot is produced in this termination step, because this is predominating in the high pressure region. Okay. So, this will again react with H2 producing, this will react with H2 producing H2O and OH dot. So, OH dot means this situation. Okay. So, it is again an explosive situation. I hope that this explains this particular representation of H2 plus O2 producing 2H2O. Okay. So, branching of chain leads to explosion can be easily understood by taking this water formation from H2 plus O2. Okay. So, as I told you, as I mentioned in the earlier slides, that initiation, propagation, branching. So, these are the typical steps in chain reaction. So, chain reaction must have this initiation. A typical example is C2H6 gas producing 2CH3 dot. Then propagation. Okay. Then propagation. Propagation means this is propagated, that is CH3 dot plus C2H6 producing another radical and CH4 is produced. So, this will continue. Branching, as usual, this is a branching situation. So, this branching, this is one example of branching. Retardation, as I told you, that if more of HBr is produced, more of HBr is produced means it is the retardation, that will retard the reaction. Termination, when two say Br dot or maybe two CH3 CH2 dot are combining, they will produce one non-radical species. That means it is a termination step. Inhibition means that will act as an inhibitor. Okay, this is similar to retardation. Okay. So, a chain reaction will have initiation, propagation, termination, retardation, okay, branching and maybe inhibition. Okay. Now, let us move on to polymerization kinetics. So, what do you mean by a polymer? All of you heard about molecules, say H2, okay, say maybe water, maybe oxygen. So, these are all examples of a single molecule. I mean, if you have water, means in a glass of water, you will be finding that everywhere you will be getting monomer of H2O. Maybe they are a little bit associated because of hydrogen bonding, okay, but that is not a true chemical linkage. Okay. Even if you go to say hydrogen gas, it will be, if we have a chance to look into this gas molecules, although it is not possible because it is gas molecules are too small to be detectable by our eyes. We should find there, means if we look into, we should find that every molecule will be H2. So, these are all examples of monomers. Okay. Now, if we say move from monomer to a situation that two molecules, say some anhydride like acetic acid, acetic anhydride. So, if you take out water from two molecules of acetic acid, you will be generating acetic anhydride, which is in a true sense a dimer of you will be generating acetic anhydride, which is a true sense of, in true sense, a dimer of acetic acid. So, it is the case of dimer. In the same way if you keep on adding one unit after another, there is one unit then another unit, like brickwork to produce to generate a huge building. Okay. So, you will be generating a huge huge molecule, okay. So, which is nothing but it will become a dimer, trimer, tetramer, pentamer and so on. Ultimately, it will be an n, I mean n means n number of monomer combination, which is called the N-mer, or which is also called as polymer, that is polymonomer is called the polymer. Like a protein is a biopolymer. So, it consists of 20 naturally occurring amino acids. So, if you look into any protein like hemoglobin, it is also a metalloprotein. It contains a metallic prosthetic group, that is iron 2 prosthetic group, plus which is embedded, this iron 2 prosthetic group is embedded within a polymeric framework, which is called the protein backbone or protein matrix. So, this protein matrix is consisting of a combination of this a specific combination, which is called a sequence, a specific combination of these monomers. So, protein is a biopolymer. Okay. So, and also in day to day life, like plastic or maybe we call polythene, it is also a polymer. So, it is polyethylene. Okay. So, polythene is a polymer, plastic it is also another polymer. So, these are all called polymers. So, polymerization, if we look into polymerization kinetics, okay. So, the process by which this polymer is generated is called the polymerization. Okay. So, polymerization kinetics we have to look into, since we deal with in this particular series of lectures the rate process. So, one is called the chain polymerization and the second one is called the stepwise polymerization or polymerization. Okay. So, what is called chain polymerization? Now, it is basically you can say like this: an activated monomer attacks another monomer, okay, or one activated monomer reacts with another monomer and forms a chemical linkage, a chemical bond, okay, with the second monomer, thereby producing a dimer. Okay. Then this whole dimer is again acting as a reactant to attack the third monomer to produce a trimer and so on. So, in this way monomer becomes a dimer, dimer becomes a trimer, trimer becomes a tetramer, and it will continue for a long time. And if you allow the reaction to occur for a long time, then you will be ending up with a situation, that is, you will be able to generate a giant molecule having n monomers. They are chemically linked with one another, which is called a polymer. So, it is called this process is called a chain polymerization, that is, this reaction occurs in a chain of sequences, one after another, one after another. Okay. What happens in case of stepwise polymerization? Now, in this case the reaction where this stepwise polymerization is occurring, that is a sequential polymerization is occurring, that is one after another. So, in steps. So, in this case small molecules like water gets eliminated, okay, from the from the reaction mixture or from reaction from the reaction medium. Okay. So, A plus another B producing a a dimer, say AB plus water or maybe a small molecule. It is called the stepwise polymerization. Okay. Now chain polymerization is it generally requires a chain initiator, like I told you that like this H2 plus Br2 reaction, that initially you need to generate 2 Br dots, 2 Br radicals. So, that is your initiation step, and that radical, that Br dot radical is used up to do further propagation steps. So, in this case also for chain polymerization reaction, now this requires some initiator which initiates your reaction. Okay. So, in this case it has been found that this reaction rate is first order in monomer and to the power half in initiator. So, your rate is proportional to your monomer and initiator I to the power half. Okay. So, then we would like to define one quantity which is called the kinetic chain length, okay, which is called nu KCl, nu kinetic chain length. It is nothing but the measure of the efficiency of the chain propagation reaction. How efficiently this chain is propagated, because propagation is very important for further processing. Like if you do not have a very long propagation, if it does not propagate for a long time, then longer molecules cannot be formed. That is, the molecules having huge chain length will be difficultly formed. Okay. So, this is defined in this way, that is nu P divided by nu I, which is nothing but the number of monomer units consumed in the numerator divided by the number of active center produced. Active center means the centers, like a radical center may be an active center, or the center which is active for doing further reaction. So, this ratio is called the kinetic chain length. Now, let us come to this mechanism of this, a general mechanism for this. Okay. What is that? Now, initiator, okay, initiator I producing 2 R dot, maybe 2 radicals, because generally like Br. So, if you initiate, then it will be generating 2 Br dot, okay, or maybe say peroxide, say like this, something is there, something is also there. So, if you do a homolytic cleavage, then you will be generating 2 radical centers over here. Okay. That is why 2 R dot, or it may be M plus R dot producing another radical. So, initiation rate is equal your K I times concentration of I. Remember, this is your elementary step, it is not the overall rate, it is the rate for the elementary step. Okay. So, next come to propagation, that monomer plus monomer 1, okay. Monomer 1 means M1 maybe, okay. So, producing something MR2, monomer 2 I mean M2 means it is another monomer is combined with M1, then M plus M2 producing M3, M plus M3 producing M4 in this way. So, nu P or Vp is equal to Kp, so rate constant times, since two species are involved. So, therefore, one monomer concentration will be there and one n minus 1 mer. So, if this reaction, if a reaction is producing nth mer, I mean a polymer with n number of monomers, therefore, for that reaction you can write your rate expression which is equal to some constant times monomer into the concentration of Mn minus 1 dot, okay. And there is a termination step also, that M plus M3 may be M4, which is the termination step, okay. It may be something else also, it is just a you know representation. So, rate of termination is K termination times say M dot square, because 2 M dot is giving rise to you know another product. So, therefore, you may put a dot over here maybe, and you may remove this dot, okay. So, because it is a termination means two radicals must combine. So, here this dot may be somehow moved over here. So, anyways you may put a dot over here, or maybe one M dot another M dot producing M2, that may be another thing, okay. So, important thing that not all initiator molecules produce chains, it is very important point, and phi is the fraction of another thing, we are using another quantity phi, the fraction of initiator molecule that produce chain, okay. That means important concept that we have to invoke over here, that any initiator may not lead to chain reaction or may not lead to further propagation of a chain. And also another point is that 100% you know initiator molecules are not used up to produce chains, maybe some fraction is lost. So, to account for that fraction you have to put a quantity like here this one KII. So, you put 2 phi KII ddt of M dot, okay. So, it takes into account of you know this probability of producing a chain, okay. So, in terms of kinetic chain length, you know you have to write in terms of Kt and Kp, okay. So, Kt in terms of Kt and in terms of Kp you have to write, okay. So, what you can write? So, in that case in terms of, if you want to write in terms of Kt and Kp, you will be getting this expression. If you put the appropriate numbers over here, appropriate expression over here, you will be generating, you will be getting this expression, that your VKCl kinetic chain length will be like it is a first order in M and half order in I, initiator, concentration of the initiator, okay. Now, next we will come to stepwise polymerization. A classic example of a stepwise polymerization is you know nylon production, okay. So, now let us take this example. So, NH2 CH2 whole 6 NH2, and you know this is basically the formation of CONH. It is you know a peptide bond formation, okay. Not, it should not be, it is an amide bond formation, okay. So, this peptide amide bond is there in proteins, kind of peptide bond formation. So, this NH2 reacts with this one. Okay. So, therefore, producing this 4 CH2 containing this one and 6 CH2 containing this one, they are condensing to produce this one plus water. So, after many steps, what is happening? After many steps, it will be n number of this whole unit, n number of whole unit, of which in one side there will be NH2 and the other side there will be COOH. So, this side will be called as carboxy terminus, carboxylated terminus or carboxy terminus, and this side is amino terminus. Okay. Now, rate law, suppose A is equal to concentration of concentration of COH. So, A can be taken as any generic terminal group for polymer undergoing condensation. So, rate of polymer formation will be your this unit and that unit. Okay. So, this will be basically, this will go as A square. Okay. Minus sign is simply because of something is used up or whether something is generated. Okay. So, and if the rate constant is independent of molar mass of the polymer, then you can express this as this one. Okay. So, what we have learned today in this lecture. So, let us go back that it is a complex reaction. We have started with types of complex complex chain reaction. We talked about chain reaction. Then we have taken H2 plus Br2 reaction and why it is a fractional order with respect to Br2. We have also explained it we using this mechanism. Then we moved on to explosion. Okay. Then we moved on to this branching reaction, I mean branching of chain which leads to explosion. We have taken a classic example of H2 plus O2 producing H2O, and the mechanism is also talked about in details, and the factors that affect this process, whether explosion will take place or not, that we can explain very well. Now, then we talked about this basic characteristics of chain reactions. Okay. Then we started with polymerization kinetics, and there are two types of kinetics. One is chain polymerization, another is stepwise polymerization. And chain polymerization we talked about in terms of kinetic chain length. We have also tried to talk about a little in terms of mechanism, and then kinetic chain length, how this can be calculated, that is also talked about. And finally, we came to the conclusion that your overall rate, that is kinetic chain length, is first order in monomer concentration and half order in initiator concentration. So, in our next lecture, we will focus probably that will be the last lecture, probably I am not sure, I have to think of anyway, but probably that will be the last lecture for complex reaction. Then we will move on to theory of reaction rates. So, we will have that in the next lecture, that is complex reaction continued. So, I hope in the next lecture we should be able to complete complex reaction. So, till then, have a nice time. Thank you.